Okay, let's jump right in. Today, we are doing a deep dive on an organism that, let's be honest, is probably showing up on your radar more and more. Achromobacter xylosoxidans. And look, this isn't just another non-fermenting gram-negative rod. No, this is a bug that's really forcing us to rethink our entire approach, all the way from the lab bench straight to the patient's bedside.
You know, for the longest time, this bacterium was kind of written off as just environmental noise. A contaminant, a curiosity on a culture plate. But that perspective is not just outdated, it's downright dangerous. Achromobacter xylosoxidans has really stepped into the spotlight as a serious threat, a formidable pathogen that preys on our most vulnerable patients, especially those with cystic fibrosis or hematologic malignancies. So, to put this all together for you, we've used Gemini Deep Search to synthesize the absolute latest research and clinical guidelines. All the fantastic visuals you'll see are from Microbe Canvas. And for all of you who want to go even deeper, and I know you're out there, we've compiled all the primary references for you in a linked notebook.
So here's our roadmap. We're going to follow the path from the bench to the bedside. We'll start with why Achromobacter xylosoxidans is such a rising threat. Then, we'll get into the nitty-gritty of lab ID, break down its clinical impact, and then wrestle with the really tough treatment challenges. And we'll finish up with a critical look at prevention, control, and what the future holds.
First up, a rising threat. So how on earth did this organism go from being a background player to a main character in our clinical microbiology drama?
And this right here, this is where it gets incredibly real. We're not just talking about a bug finding a place to live. In patients with cystic fibrosis, chronic carriage of Achromobacter xylosoxidans is a massive red flag. It is a direct predictor of worse outcomes. We're talking a faster drop in lung function and more frequent, more severe exacerbations. This right here is why getting the identification and the management absolutely right is so critical.
Okay, let's shift gears and head over to the lab. Section 2 is all about definitive laboratory identification. Because let's face it, getting the idea right is the cornerstone of everything that comes after. And as you're about to see, it is not always a walk in the park.
You know, this organism has had a bit of an identity crisis in its past. If you've been in the field for a while, you might actually remember it as Achromobacter xylosoxidans. This timeline really tells the story of its taxonomic roller coaster, from its first description to that brief stint in the Achromobacter family, and then its rightful return to Achromobacter, all thanks to 16S RNA sequencing. Knowing this history is key if you're ever digging through older research.
Now, at the bench, Achromobacter can be a real chameleon, often looking a lot like other non-fermenters. The trick is to know its tells, especially when you're comparing it to something like Pseudomonas aeruginosa. Think of it like this. Achromobacter has flagella all over its body, while Pseudomonas just has them at one end. Achromobacter is non-hemolytic, but Pseudomonas often is. And while Pseudomonas loves to show off with those classic blue-green pigments, Achromobacter is plain. No color, no metallic sheen. Oh, and here's a curveball. It can grow on BCSA, which can sometimes make you think you're looking at Burkholderia. Sneaky.
So what's the gold standard for a definitive ID today? While the modern approach is a pretty clear three-step ladder. We might start with traditional phenotypic systems like Vitek or API, but, and this is a big but, they are notoriously unreliable for this bug and often get it wrong. The next step up, MALDI-TOF, is great. It's fantastic for getting you to the Achromobacter genus. But for the ultimate definitive species-level answer, especially when you're dealing with an outbreak or a really tough case, you have to bring out the big guns, nRDA gene sequencing. That's the gold standard. Okay, so we've covered the what. Now let's get to the so what. Section 3, clinical impact and disease. We've got the ID, but what kind of damage can this thing actually do to a patient? This chart here paints a really clear picture of where Achromobacter hits the hardest. A whopping 50% of its damage is done in the lungs of cystic fibrosis patients. Another 30%? That's bloodstream infections, usually in immunocompromised patients, like those with blood cancers. The rest is kind of a mix of hospital-acquired pneumonias and other infections, often tied to things like catheters and other medical devices.
So what's its secret? How does it become such a successful pathogen? This slide really breaks it down. Achromobacter is a master of survival. It builds these incredible, fortress-like biofilms that shield it from antibiotics and our immune system. It uses sophisticated secretion systems to literally inject proteins into our cells and manipulate them.
It also triggers this massive inflammatory response that ends up causing a lot of collateral damage to our own tissues. And of course, its ultimate weapon? A built-in, natural resistance to multiple drugs right from the get-go.
And that leads us perfectly into our next huge challenge, Section 4, the treatment conundrum. This is really where the rubber meets the road for the entire clinical team.
To really get why treatment is so hard, we have to talk about its intrinsic resistome. This isn't about the bug learning to be resistant. Achromobacter is basically born with it. It's got these efflux pumps that act like little bouncers at a club door, just kicking antibiotics right back out of the cell. And it produces its own beta-lactamase, OXA114, that chews up our drugs. This is exactly why so many of our go-to therapies just don't stand a chance.
And if you look at the latest EU cast breakpoints, the story gets even more sobering. Our list of reliable weapons is really short. Pip-Tazo, Meropenem, and Trimsulfa are our main options. But look closely at what's missing. There are no clinical breakpoints for ciprofloxacin or colistin, and that's a huge deal for the lab because it means we can't confidently tell a clinician if those drugs will work, no matter what the MIC value says.
Now this is where things get really clever. The Dutch SWAB and NVALT guidelines don't just throw drugs at the problem. They get strategic. They recommend high doses, sure, but the key is the extended infusions. We're talking a 3-hour infusion for Meropenem and a 4-hour one for Pip-Tazo. It's all about pharmacokinetics, playing the long game, keeping that drug concentration above the MIC for as long as possible to really deliver a knockout blow.
So you've got the Dutch approach, which is all about maximizing the power of our core beta-lactams. But what about the rest of the world, especially when you're up against a highly resistant strain? That's when we start hearing about salvage therapies. This is where we bring in the newer, more specialized weapons like cefiderocol, the so-called Trojan horse antibiotic, or ceftazidime-avibactam.
And just when you thought it couldn't get more complex, let's talk about treating kids with CF. We are up against a phenomenon called hyperclearance. Essentially, their bodies are like super efficient drug-clearing machines. So what does that mean in the real world? It means a standard pediatric dose is going to fail. The drug levels just won't get high enough for long enough. It's a recipe for disaster.
And this is how we fight back. Look at this. For Meropenem, we literally double the dose from 20 mg per kg up to 40, and we still use an extended infusion. For Pip-Tazo, we shorten the dosing interval to every 6 hours to keep those drug levels where they need to be. It's an aggressive, high-dose strategy, but it's exactly what it takes to win the battle in these kids.
All right, let's bring it all home with our final section, Section 5, Prevention, Control, and Outlook. So, how can we get ahead of this bug and actually stop these infections before they even have a chance to start?
This right here is the million-dollar question for every infection control team out there. Achromobacter is a true water bug. It loves to set up shop in our sink drains, our shower heads, our faucets. And here's the kicker. It can actually survive, and in some cases even thrive, in disinfectants we rely on, like chlorhexidine. That means our standard cleaning playbook might not be enough.
To take on a challenge this big, you need a multi-pronged attack. First, you have to manage the water. That means things like using point-of-use filters on taps and showers, especially in high-risk units. Next, you go after the environment. You know, something as simple as regularly flushing water outlets can make a huge difference in stopping biofilms from building up. And finally, you have to manage the patients. In places like CF centers, this means having really strict segregation protocols to stop the bug from spreading person to person.
And if you need a chilling reminder of just how dangerous this bug can be when things go wrong, just look at this devastating case. A major outbreak was traced back to a healthcare worker who was diverting narcotics and replacing the stolen drugs with contaminated saline. They were, in effect, injecting Achromobacteria directly into their patients' veins. It is a horrifying example of how this organism will exploit any weakness, any breach in our defenses.
So there you have it. Achromobacter xylosoxidans has gone from a footnote in the back of a textbook to a major clinical player. Taming this bug takes a combination of smart diagnostics, aggressive and clever treatment, and absolutely rock-solid infection control. This is a story that's still evolving, so make sure you subscribe to stay on top of the latest. And now we really want to hear from you. What's your experience with this tough pathogen? Share your stories, your challenges, your successes in the comments below. Let's learn from each other and take on this challenge together.